Hello students, in this video I am going to prove fundamental theorem of integral calculus. This theorem has two parts. Here I am going to prove part 1. Statement of part 1 is that lowercase f at x is a continuous function on the interval AB and uppercase f at x is defined as integral a to x ft dt. Then derivative of uppercase f of x is equal to lowercase f at x. Let us prove this part. Here I am going to draw a graph. Y-axis, and take this is t. Let's say the function f dt. Suppose this is the line t equals to a small a, and somewhere take here b unit. This line is t equals to b. Next, we have uppercase function f at x defined as integral a to x f at x, f t dt. By Riemann integral, what is this? This represents to the area between the curve and the line, say this is x. This integral represents to the area from a to x and under the function ft dt, and we shade this area like this. So this the shaded area is represented by the integral a to x ft dt. Now, by first principle, derivative of f at x can be written as limit delta x approaches to 0 f of x plus delta x minus f at x divided by delta x. This is the by definition of first principle. This can be written as limit delta x approaches to 0, and by definition of f we write here integral a to x plus delta x ft dt minus integral a to x ft dt divided by delta x. Next, you see here, this represents to one area and this represents to one area. When we subtract this area from this area, we left with some other area. Now, let us suppose x plus delta x is here. X plus delta x. Now we use some other color to represent the area. Now you see the integral a to x plus delta x ft dt represents to the area shaded in brown, a to x plus delta x, and the integral a to x ft dt represents to the area shaded by blue lines. So when we subtract the blue area from the brown area, we left with the area only between x and x plus delta x, only between this strip. So we can write it as limit delta x approaches to 0. This difference can be written as integral x to x plus delta x f at t dt. And here we can write 1 by delta x. Once again, understand this. This difference represents to the area left only with this strip between x to x plus delta x. When we subtract the blue area from the total brown area, we left with this area x to x plus delta x. That's why we write this one in the integral form x to x plus delta x ft dt. Now, by mean value theorem of definite integral there exists a point C. There exists a point C between x and x plus delta x such that f at c into delta x represents to the area of the strip x to x plus delta x whose height is, let us say here is C. C lies between x and x plus delta x. Then when we find the value of f of t at C, then this is the height of, this is Fc. The height of this strip becomes Fc and the width is delta x. So its area is Fc into delta x. This is a simple formula of rectangle, length multiplied breadth. So height is, you can say this is the length Fc and width is delta x. So its area is Fc into delta x. In integral form, the same area of this strip can be written as integral x to x plus delta x ft dt. So we can write Fc into delta x equals to we can write Fc into delta x, or in other words, we can skip from here. Now, Fc into delta x equals to integral x to x plus delta x ft dt. Once again, I repeat the process. By mean value theorem of different integral, there exists a point C between the interval x to x plus delta x such that area of this strip x to x plus delta x is the width, x to x plus delta x, whose width is delta x and height is Fc. It will be represented by Fc into delta x. And also the area of this strip in integral form can be written as x to x plus delta x ft dt. So both area represents to the same area of the same strip. So we can write it as this area equals to this area. Now take limit delta x approaches to 0, Fc, this becomes divided by delta x here, 1 by delta x integral ft dt. Here is the limit x approaches to delta x. Like some congestion. Limit delta x approaches to 0, Fc equals to limit delta x approaches to 0, 1 by delta x, x plus delta x, f of t dt. Here we divided by delta x. So this becomes what it is. when delta x approaches to 0, c approaches to x, or we can write equivalently c is equal to x, or we can apply the sandwich value theorem. So this quantity becomes f(x), f at x, and this is equal to, what is this? In the last result, this one is equal to f dash x, capital F dash x. So we proved uppercase f dash x or derivative of uppercase f at x equals to lowercase f at x. This proves the theorem. And why it is known as fundamental theorem of integral calculus? As it establishes the relationship or makes a connection between the derivative and the integration, or the antiderivative. So in other words, we say if f of x is a continuous function in some interval, it always have a antiderivative in that interval. So that's why it is known as fundamental theorem of integral calculus. It makes a connection between the derivative and the integration. In the other theorem, we will discuss regarding the second part of fundamental theorem of integral calculus. Thank you.